Alrighty, let's get started back on this chapter. So we're doing a line sorting program here. Let's just go over the code from the start here. So pound includes standard IO and string, defines max lines as 5,000, which is the size of the pointer to the text lines. Okay, that makes sense. And then we forward declare the readlines function, which takes in the line pointer and how many lines we want to read, I guess, and returns an integer. And then write lines takes in similar arguments, returns void, writes things out. And then we have a Q sort, takes in the line pointer array and a left and a right. It can be called recursively, sort the lines. So in our main, we have an integer counter for the number of lines to be read. No, sorry, the numbers of lines that we did read. We call read lines up to the max, and we say, hey, if the n is greater than or equal to 0, then we're going to quick sort. It really should be greater than or equal to 1, or just greater than, it should be greater than 1. Because if there's only 1 or 0, you don't want to quick sort it, right? Like I said, it doesn't matter if you quick sort it. Simplifies the code a bit here. Alright, so you quick sort it. We give it the same array of line pointers. We sort from 0th element to the number of lines minus 1. And then we write lines, and then we return 0. And if there were no lines to read because it was less than, or yeah, it was less than 0, so not only were there no lines to read, but there was an error, then we print out error too big, input too big to sort, and return 1. That's pretty basic error handling there. And then the next function over here, we define the max length of each line is going to be 1,000. And then we forward declare get line, which is a chart. Get line, you give it a char star, and it gives you back an integer. And then alloc. Okay. So these are read lines and write lines. So read lines, we basically go into a loop where we get each line, and it gives it back our length. Okay, that makes sense. And then so while that is greater than 0, so there's work to be done. Then we say if number of lines is greater than or equal to max lines, or our allocation is null, then we return -1. That's interesting. Okay, so that means that if we get to else, then P has been allocated. That's a rather weird way of doing it, but it works because OR is a default operator. So then we go into our else case. We say, hey, length len minus 1. We're going to just boop, delete that new line, and replace it with a null terminator. And then we do a stir copy into, wait a minute, from line into P. So now we have just a heap allocated bit of memory called P, and we add that to our line pointers, and then we increment our end lines to go to the next line, and then return it. Right lines, we just go through each end line. We index the line pointer I, which then dereferences that and gives us the value there. And we print that out. Okay, that makes sense. The function getLine is from section 1.9. The main thing is the declaration of line PTR. Say that line PTR is an array of max line elements, each element of which is a pointer to a char. That is, line pointer I is a character pointer, and dereference line pointer I is the character it points to, the first character of the ith saved text line. Since line pointer is itself the name of an array, it can be treated as a pointer in the same manner as our earlier example, and right lines can be written instead as right lines I like the first version better, to be honest. Some of this pointer stuff is just, I don't know, it's not very intuitive. Initially, the line pointer points to the first line. Each increment advances it to the next line pointer, while end lines is counted down. With input and output control, we can proceed to sorting. The quick sort from chapter 4 needs minor changes. The declarations have to be modified, and the comparison operation must be done by calling strcomp. The algorithm remains the same, which gives us some confidence that it will still work. Similarly, the swap routine needs only trivial changes, since any individual element v as line pointer in a character pointer temp must be also so. No, wait a minute. Since any character, sorry, let me reread this. Since any individual element of v, alias line pointer, is a character pointer, temp must be also. So one can't be copied to the other. Jesus Christ. All right. Exercise 5.7. Rewrite read lines to store lines in an array supplied by main, rather than calling alloc to maintain storage. How much faster is a program? Okay. Multidimensional arrays. C provides rectangular multidimensional arrays, although in practice they are much less used than arrays of pointers. In this section, we will show some of their properties. Consider the problem of date conversion from day of the month to day of the year and vice versa. For example, March 1st is the 60th day of a non-leap year and the 61st day of a leap year. Let us define two functions to do the conversion. Day of year converts the month and day into the day of the year, and month day converts the day of the year into the month and day. Since this latter function computes two values, the month and day arguments will be pointers. Say, hey, month day, 1988, 60, give me the month and day. Sets M to 2 and day to 29. February 29th because it's a leap year. These functions both need the same information: a table of the number of days in each month, 30 days, half September. Since the number of days per month differs for leap years and non-leap years, it's easier to separate them into two rows of a two-dimensional array that can keep track of what happens to February during computation. The array of the functions performing the transformation as follows. Okay. It's a bit strange because you have the 0th index. So you have to have 13 elements, and everything's identical except for February. How I would implement it, but to each their own. Day of the year takes in the year, month and day, gives you back the day of the year. So this is where we do a little bit of math to figure out if it's a leap year, and then we use leap to index into the array, and then we can then go ahead and index into I because you start at 1. Yeah. Adding up those days and then return the day total. So take for an example January 15th, and the leap year we don't really care about. So we would go into here and we'd say I is less than month, so I is 1. So we'd skip over January and then we just return 15th. So say February 15th. So then we go in here, we would say I is equal to 1. I, which is 1, is less than month, which is 2, which is true. So then we would go down here and we would grab out February's days, which are 28 or 29, add them to the 15th, and then return it. Say it was 3. Then we would go through, do it for February and March. Yep, that works. Okay. Month day. Set month and day of the year. And set month day from day of the year, to inverse of that. Okay. We call that arithmetic value of a logical expression, such as the 1 for leap, is either 0 false or 1 true. So it can be used as a subscript of the array day tab. The array day tab has to be external to both day of the year and day of the month, so that it can be used so that both can use it, obviously. We made it char to illustrate a legitimate use of char for storing small non-character integers. Day tab is the first two-dimensional array that we have dealt with. In C, a two-dimensional array is really a one-dimensional array, each of whose elements is an array. Hence, subscripts are written as daytab ij row column rather than daytab I comma j. Other than this notational distinction, a two-dimensional array can be treated in much the same way as in other languages. Elements are stored in rows, so the rightmost subscript or column varies fastest as elements are accessed in storage order. An array is initialized by a list of initializers and braces. Each row of a two-dimensional array is initialized by a corresponding sublist. We start the array day tab with a column of 0 so that both month numbers can run from the natural 1 to 12 instead of 0 to 11. Since space is not a premium here, this is clearer than adjusting the indices. If a two-dimensional array is to be passed to a function, The parameter declaration in the function must include the number of columns. The number of rows is irrelevant since what is passed is, as before, a pointer to the array of rows, where each row is an array of 13 ints. In this particular case, it is a pointer to an object that are arrays of 13 ints. Thus, if the array datetab is to be passed to a function f, the declaration of f would be 213. It could also be arbitrary 13, since the number of rows is irrelevant, or it could be datetab, datetab dereferenced 13 int. What? The hell? Which says that the parameter is a pointer to an array of 13 integers. The parentheses are necessary since the brackets have higher precedence than star. Without parentheses declaration, so-and-so is an array of 13 pointers to integers. That's what I would interpret, yeah. More generally, only the first dimension subscript of an array is free. All the others have to be specified. Section 512 has further discussion on complicated declarations. Exercise 5.8, there is no error checking of day of year, month, day, remedy this defect. No, thank you. Initialization of pointer arrays. Okay. Consider the problem of writing a function month name n, which returns a pointer to a character string containing the name of the nth month. This is an ideal application for the internal static array. Month name contains a private array of character strings and returns a pointer to the proper one when called. This section shows how that array of names is initialized. The syntax is similar to previous initializations. So you got month name int n, static char, okay. The declaration of name, which is an array of character pointers, is the same as line pointer. In a sorting example, the initializer is a list of character strings. Each is assigned to the corresponding position in an array. Characters of the ith string are placed somewhere, and a pointer to them is stored in name sub I. Since the size of the array name is not specified, the compiler counts the initializers to fill in the correct number. Pointers versus multidimensional arrays. Newcomers to C are sometimes confused about the difference between a two-dimensional array and an array of pointers, such as name in the example above, given the definition A1020 or B10, which is a pointer. It's fragmentation. The A1020 is going to be in a contiguous amount of memory, whereas B can point anywhere. Then A34 and B34 are both syntactically legal references to a single int, but A is a true two-dimensional array. 200 int-sized locations have been set aside, and the conventional rectangular subscript calculation is used to find the element. For B, however, the definition only allocates 10 pointers and does not initialize them. Initialization must be done explicitly, either statically or with code. Assuming that each element of B does point to a 20-element array, then there will be 20 ints set aside plus 10 cells for the pointers. The important advantage of the pointer array is that the rows of the array may be different lengths. That is, each element of B need not point to a 20-element vector. Some may point to 2 elements, some to 50, and some to none at all. Although we have phrased this discussion in terms of integers, by far the most frequent use of arrays of pointers is to store character strings of diverse lengths, as in the function monthName. Compare the declaration and picture for an array of pointers. With those for a two-dimensional array. makes sense. Exercise 5.9. Rewrite the routines day of year, month, day with pointers instead of indexing. Do not care about that. Command line arguments. So this is a bunch of arrays of pointers. Environments that support C. There is a way to pass command line arguments or parameters to a program when it begins executing. When main is called, it is called with two arguments. The first, conventionally called argc, or argument count, is the number of command line arguments the program was invoked with. The second, argv, is this argument vector, is a pointer to the array of character strings that contain the arguments, one per string. We customarily use multiple levels of pointers to manipulate these character strings. Simplest illustration is the program echo, which echoes its command line arguments on a single line separated by blanks. That is, the command prints so-and-so prints the output hello world. By convention, argv0 is the name by which the program was invoked. So argc is at least 1. If argc is 1, then there are no command line arguments after the program name. In the example above, argc is 3. And arg0, argv1, argv2 are hello, echo, hello, and world, respectively. The first optional argument is argv1, and the last is argc minus 1. Additionally, the standard requires that argc be a null pointer. Yeah, I ran into that. The array is null terminated as well. The first version of echo treats argv as an array of character pointers. So you go over every value of argc. And say, hey, argv, I'm going to print you out. And if it's the last one, or if it's not the last one, then we print out, we add an extra space on it. And at the end, we print a new line. Since argv is a pointer to an array of pointers, we can manipulate the pointer rather than index the array. The next variation is based on incrementing argv, which is a pointer to char, while argc is counted down. So, say while argc decremented is greater than 0, then we take argv. Yeah, we're going to increment it because we don't want that first element. Just say argv plus plus and then dereference. And then if argc is greater than 1, then we put a space. Yeah, makes sense. Since argv, I prefer the first syntax, to be honest. I think it reads cleaner. You're using the array indexing than the pointer arithmetic. Like this star plus plus versus like, okay, I'm subscripting, getting the element out. And then this, yeah, you're mutating argc. It's like, I don't really feel like we should be mutating it. I mean, it's our argc, we can do whatever we want with it, but it seems weird. Since argv is a pointer to the beginning of an array of an argument string, incrementing it by 1 makes it point to the original argv1 instead of argv0. Each successive increment moves it along the next argument. Star argv then is a pointer to that argument. At the same time, argc is decremented when it becomes 0. There's no arguments left to print. Alternatively, we could write printf statement as printf. Yeah, that's an alternative way of doing it. This shows that the format argument for printf can be an expression too. Obviously. As a second example, let us make some enhancements to the pattern finding program from section 4.1. If you recall, we wired the search pattern deep into the program, an obviously unsatisfactory arrangement. Following the lead of the Unix program grep, Let us change the program so that the pattern to be matched is specified as the first argument in the command line. This is just so silly. I feel like I can just skip over all this stuff. Alright, we're almost at the end here. And we're getting into some actually interesting stuff. I'm going to skip this program because it's not interesting to me. The standard library function stir returns a pointer to the first occurrence of the string t in the string s, or null if there is none. It is declared in string.h. The model can now be elaborated to illustrate further pointer construction. Suppose we want to allow two optional arguments. One says print all lines except those that match the pattern. Second says precede each printed line by its line number. A common convention for C programs on Unix is that an arrangement that begins with a minus sign introduces an optional flag or parameter. If we choose -x for accept to signal the inversion and -n number to request line numbering, then the command find -x-n pattern will print each line that doesn't match the pattern preceded by its line number. Optional arguments should be printed in any order, and the rest of the program should be independent from the number of arguments that were present. Furthermore, it is convenient for users if option arguments can be combined, as find -nx pattern. Here's the program. You should just use argparse, bro. Like, we're not going to do all this crazy stuff. argc is decremented and argv is incremented before each optional argument. At the end of the loop, if there are no errors, argc tells how many arguments remain unprocessed, and argv points to the first of these. Thus, argc should be 1, and *argv should point to the pattern. Notice that * plus argv is a pointer to an argument string, so * plus argv 0 is the first character. An alternative valid form would be ** plus argv, because bracket binds tighter than * and plus the parentheses are necessary. Without them, the expression would be taken as argv 0. Okay. In fact, that is what we used in the inner loop, where the task is to walk along a specific argument string. In the inner loop, the expression * plus argv 0 increments the pointer to argv 0. The pointer argv 0. Okay. It is rare that one uses pointer expressions more complicated than these. In such cases, breaking them into 2 or 3 steps will be more intuitive. Thank you. Write the program expr, which evaluates a reverse Polish expression from the command line, where each operator or operand is separate argument. For example, not doing that. Modify the program's en tab and d tab, written as exercises in chapter 1. So yeah, modify the program's en tab and dn tab, written as exercises in chapter 1, to accept a list of tab stops as arguments. Use the default tab settings if there are no arguments. Extend en tab and dn tab to accept the shorthand. Don't care about this. Write the program tail, which prints the last n lines of its input. By default, n is 10. Let us say, but it can be changed by an optional argument, so that tail minus n prints the last n lines. The program should behave rationally no matter how unreasonable the input or the value of n. Write the program so it makes the best use of available storage. Lines should be stored in the sorting program of section 5.6, not in a two-dimensional array of fixed size. Pointers to functions. Finally, something a little bit interesting. Function pointers. In C, a function itself is not a variable, but it is possible to define pointers to functions, which can be assigned, placed in arrays, passed to functions, returned by functions, and so on, and most importantly, called. We can illustrate this by modifying the storing procedure written earlier in this chapter so that if an optional argument -n is given, it will sort the input lines numerically instead of lexicographically. A sort often consists of 3 parts: a comparison that determines the ordering of any pair of objects, an exchange that reverses the order, and a sorting algorithm that makes comparisons and exchanges until the objects are in order. The sorting algorithm is independent of the comparison and exchange operations. So by passing different comparison and exchange functions to it, we can arrange to sort by different criteria. This is the approach taken in our new sort. Lexicographic comparison of 2 lines is done by stir compare as before. We will also need a routine num compare that compares 2 lines on the basis of numeric value and returns the same kind of condition indicated as strconf does. These values are declared ahead of main, and a pointer to the appropriate one is passed to qsort. We have skimped on error processing for arguments so as to concentrate on the main issues. Okay, I'm just going to scan through here. Okay, so here's where we're doing the function pointer stuff. Also, qsort takes in the function pointer here. So that's the first time we use function pointers. So it takes in a comparison function that takes in 2 pointers of void star and returns an integer. And then when we call qsort here, we have to pass in that function. So we have the type assertion here, which this could be type def out, so it's less confusing to read. And then we say, hey, if it's numeric, use numeric comparison, otherwise use string comparison. It's a pretty basic modification. In the call to qsort, strconf and numCompare are addresses of functions, since they are known to be functions. I want to ask AI a question here. When passing in a function as a pointer to another function in C, do you have to use ampersand to get a pointer to the function? I'm guessing the answer is no. Okay. Yeah, both of these are valid. They mean the same thing. Why would anyone ever use ampersand in front of a function? Older texts, like the C programming language, sometimes include ampersand explicitly when introducing function pointers. I haven't seen that yet, because it mirrors how we take addresses to variables. But in real code today, you usually see quicksort, compare. Yeah, okay. I'm good. Okay. Here, it actually says that right here. Since they are known to be functions, the ampersand operator is not necessary. And the same way that it is not, in the same way that it is not needed before an array name. We have written qsort so it can process any data type, not just character strings. As indicated by the function prototype, qsort expects an array of pointers, 2 integers, and a function with 2 pointer arguments. The generic pointer type void star is used for the pointer arguments. Any pointer can be cast to void star and back again without loss of information. So we can call qsort by casting arguments to void star. The elaborate cast of the function argument casts the argument of the comparison function. These will generally have no effect on the actual representation, but assure the compiler that all is well. Okay. The declaration should be studied with some care. The fourth parameter of qsort is a comparison that takes 2 void stars, which says that the comparison function is a pointer to a function. Sorry, that comp is a pointer to a function that has 2 void star arguments and returns an integer. The use of comp in the line so-and-so is consistent with the declaration. Comp is a pointer to a function. Star comp is the function, and star comp with the parentheses on the right hand side is the call to it. The parentheses are needed so the components are correctly associated. Without them, says that comp is a function returning a pointer to an int, which is very different. We have already shown stir comp, which compares 2 strings. Here is num compare, which compares 2 strings on a leading numeric value computed by calling a to f. Okay, we don't really care about that. The swap function, which exchanges 2 pointers, is identical to what we presented earlier in the chapter, except that the declarations are changed to void star. A variety of other operations can be added to the sorting program. Some make challenging exercises. Okay, we're done with function pointers. I thought we would get a little bit more involved in some of the syntax. Modify the sort program to handle -r flag, which indicates sorting in reverse, decreasing order. Be sure that -r works with -n, don't care. And add the option -f to fold upper and lower case together so that case distinction are not made during sorting. For example, A and A compare equal. Add the -d directory order option, which makes comparisons only on letters, numbers, and blanks. Make sure it works in conjunction with -f. Add a field handling capability so sorting can be done on fields within lines. Each field sorted according to independent. I don't really care about any of this stuff. All right. Complicated declarations. This is probably the most interesting part of this chapter. And we got 1, 2, 3, 4, 5 pages on complicated declarations. C is sometimes chastised for the syntax of its declarations, particularly ones that involve pointers to functions. The syntax is an attempt to make the declaration and the use agree. It works well for simple cases, but it can be confusing for harder ones because declarations cannot be read left to right, and because parentheses are overused. The difference between a int pointer f, which is a function returning a pointer to int, and int pointer pf, which is a pointer to a function returning an int, illustrates the problem. Star is a prefix operator and it has lower precedence than parentheses, so parentheses are necessary to force the proper association. Although truly complicated declarations rarely arise in practice, it is important to know how to understand them and, if necessary, how to create them. One good way to synthesize declarations is in small steps with typedef, which is discussed in section 6.7. As an alternative, in this section we will present a pair of programs that convert from valid C to a word description and back again. The word description reads left to right. The first DCL is more complex. It converts a C declaration into a word description in these examples. Okay. I didn't think they would actually write a program that does this. All right. In these examples, this is a pointer to a car. Yeah. This would be a function. Is a pointer to a function. No, this is a array. Pointer to an array event. This is going to be a array of 13 of pointer to int. Let's see what this one is. Void star comp, which is a function that returns a void pointer, or pointer to void. This next one is a function pointer that returns nothing. And then this is where it starts getting confusing as hell. Okay, I don't understand any of these last two examples. They're too confusing for me. Decl is based on the grammar that specifies a declarator, which is spelled out precisely in Appendix A. So it's section 8.5 in its simplified form. Decl is options, optional stars, and a direct decl. A direct decl is a name, a decl, a direct decl with parentheses on the right hand side, or a direct decl with optional signs. In words, a decl is a direct decl, perhaps preceded by asterisks. A direct decl is a name or a parenthesized decl, or a direct decl followed by parentheses, or a direct decl followed by brackets with an optional size. This grammar can be used to parse declarations. For instance, consider this declarator. Declarator. Maybe that's how you pronounce it. Declarator. So in here, this is going to be an array pointer. How does that work? There's no type information to it. I mean, if this was... Okay. PFA will be identified as a name and thus as a direct decl. Okay. Then PFA with the brackets is also a direct decl. And then the star is a decl. So all of that is a direct decl because it's next to the parentheses. Then the whole thing is a direct decl and thus a decl. You can also illustrate the parse with a parse tree like this, where direct decl has been abbreviated to direct decl. The heart of the decl program is a pair of functions, decl and dir decl, that parse a declaration according to its grammar. Because the grammar is recursively defined, the function call each other recursively as it recognizes pieces of a declaration. The program is called a recursive descent parser. Since the programs are intended to be illustrated, not bulletproof, there are significant restrictions on decal. It can only handle a simple data type like char or int. It does not handle argument types and functions or qualifiers like const. Spurious blanks confuse it. It doesn't do much error recovery, so invalid declarations will also confuse it. These improvements are left as an exercise. Here are the global variables in the main routine. Sorry, I got a hell head here. Here we are. The function get token skips blanks and tabs, then finds the next token and the input. A token is a name, a pair of parentheses, a pair of brackets, perhaps including a number or any other single character. Getch and ungetch were discussed in chapter 4. Going in the other direction is easier, especially if we don't worry about generating redundant parentheses. The program undecal converts a word description like x is a function returning a pointer to an array of pointers to functions returning char, which we express as so and so. To that. The abbreviated input syntax lets us reuse the get token function. Undecal also uses the same external variables as decal. Make decal recover from input errors. Make undecal so that it does not add redundant parentheses to declarations. Expand decal to handle declarations with function argument types, qualifiers like const, and so on. No, thank you. All right, so there's no exercises in here that I really wanted to do, unfortunately. Yeah, there's nothing here. So I think, I did learn some stuff from this chapter today, mainly around pointer arithmetic, and I was able to simplify my program that I wrote previously for the Linux programming interface, and revisit that, which is kind of nice. But yeah, there's nothing really in here that was earth-shattering novel, stuff. I think I would prefer, though, to do a little bit of research here. So I'm going to search for YouTube, C-type decal spiral. And I'm just going to go to YouTube because it's probably going to be easier just to watch a video and read a whole thing.
In this video, we're going to see the various ways of declaring pointers and
I like English as the first language. Sometimes it's hard to understand foreign speakers.
In today's video I want to talk about declaring a pointer and quirks when it comes to doing that. By now I'm sure you've realized there are at least two ways you can define or declare a pointer variable. It's not actually a pointer. Well, there is a...
This guy's the only guy talking about it, so let's do it.
So in this video, we're going to see the various ways of declaring pointers and how they are different from each other and what the meaning it conveys. The complex declaration of variables using spiral rule and all we are going to see with some C programming examples. Okay. So in this slide I have shown int star A and int star B with this kind of structure, one within the parenthesis. So for this only we're going to see the difference in this video. First, there is a rule in C which is called a spiral rule to read the complex declaration of variables. So how to read a variable? So for example, if a declaration like this cat star str in square brackets if you put up a 10 and there is a semicolon. If it's like this, you have to start always from the unknown word. Other words are known to C language. Char is a keyword, star, semicolon, square bracket, number constants, everything are known to C compiler. But str is not a keyword, it is a user defined word. So you have to start in this one and you have to read in a clockwise rule, or you can.
So the way I process this is stir is, and then I look what has highest precedence, the bracket. So I say stir is an array of tail elements, and then char star is just like, okay, it's a pointer to character. So that's the way I read it, but I don't really, in my mind, I don't do a spiral. Say stir, bracket, star, semicolon. Like, why are you going over here and then coming back over here? Wouldn't it just be like that?
So whenever a
I don't know.
bracket opens, till the bracket closes, you have to spiral like this. So for example, we start from this one, and there is a bracket opening, there is a bracket closing, and it has to come back here. Okay, so here they came back after this square closing. So we start from str, there is a square opening. How to read is str points to, I can say str is a array of 10 containing pointers, each points to a character. This is how to read it. str, there is a opening, so till closing we have to proceed. So there is a closing come here, so str, there is a opening, we read this one. str is a 10 sized array, but the array contains pointers, that each pointer, since it's the end, each pointer points to a character. So this is an array of pointers. Okay, remember, this is an array of pointers. Then each pointer in that array will be pointing to a character. So for array, if you want to find the size of this one, the array contains 10 pointers. One pointer size is 8 bytes. So the size of str will be 80 bytes. Okay, in the next example, you see this one. This is the declaration. You see which is unknown one, fp. And there is unknown you can put here also. In declaration part, here also you can put say x, I can put like this. Flow star x. So in this unknown we are starting. Okay. So f, then each pointer in that array will be pointing to a character. So for array, if you want to find the size of this one, the array contains 10 pointers. One pointer size is 8 bytes. So the size of str will be 80 bytes. Okay, in the next example, you see this one. This is the declaration. You see which is the unknown. And there is unknown you can put here also. In declaration part, here also we can put say x, I can put like this, float star x. So in this unknown we are starting. Okay. So fp, we start from here. You should not go to the left side, fp. Then you have to go to the right side, clockwise. But suddenly I reach the closing. So that means you are going back. Okay, going back till you reach the opening, and fp, and this will be put together. So fp is a pointer. That's the meaning. fp is a pointer, and then you go here. There is an opening, and you see these two things has to be kept together. Opening and this is close. fp is a pointer to a function. In this way, if parenthesis comes after the pointer, it's a pointer for a function. That you have to know. So this is a pointer, and there is a parenthesis opening, means it's a function. So in this case, there is a square opening. That's a different meaning. It's array meaning. So here, after the pointer, if there is a parenthesis opening, it's a function. So it's a pointer to a function. But what about the function? The function get these two as arguments. Okay, and then it returns the function. See this one, we got it now. FP is a pointer to a function. That function gets int and a pointer to a float as arguments. Okay, after this ending, this pair ending, it returns a pointer to a character. So how do you say this one? FP is a pointer to a function. So basically, FP is a function pointer. So FP is a function pointer. That means FP stores the address of a function. But what the function does? The function gets integer and the pointer to a float as arguments, and that function returns a character pointer. Okay, so FP is a function pointer. FP points to address of a function, points to a character. So this is spiral single array. Each single array contains here in the 2D array. The 2D array contains 2 into 4.
So again, here I would just use the precedence. The bracket operator has higher precedence. So A is a multi-dimensional array 3 by 2 whose elements are integer pointers.
So in this case, if you see integer,
this one would be A is a pointer to a array of 2 by 3 where the elements are integers. Which, if you didn't have this pointer, the asterisk here, it would still be a pointer because an array by definition is a pointer. But now it's a pointer, more explicitly a pointer, I guess.
Now I start from unknown value, unknown variable. Where it is a point here, it's containing a group of addresses. So array based on array like this. Pointers. This. So B is a array of pointers, each of which is pointing to integers. So there are 6 elements. Each element size will be a.
This will be the size of the
address
pointer.
storage. One address will be occupying
6 times that.
So it is 6 into 8. We have a 48. Okay. I'll put a backslash symbol here. So here. So we have a 24 for this one, and 48 for this. Okay. So this one will be 24 output. So here it is.
Should put his new line.
48. Okay. It's pointer to integer. Y is just a integer.
I'm interested in like really complex declarations. Doesn't seem like he's getting to any complex declarations here.
So C is we'll see with example. Straight. Okay, see this name of the array. See, we have
Okay, this is not getting into anything super complex.
Right? 780 is the starting address. This hunter is a data rather than just. What's the value of C? 1. That's why I put 1 over here. 0, 42. So 24 plus 24 plus 22, 24. So it is 72. Okay. So 72 it is moving. So it has, what is the initial value plus what you have to do? You have to do a 1 minute.
Okay. What I'm taking away from this is that the spiral rule, or whatever they call it, is kind of like not helpful. What is more helpful for me is to keep in mind precedence, because that's why you add parentheses to an expression, is to force precedence. And parentheses have the highest precedence along with the brackets. If we go back, there is a precedence table in the book, but I'm just gonna like open up a browser here and say C precedence table. And you can see parentheses and brackets along with the dot and arrow notation have the highest level precedence. Got it. And then if we look at the unary star, is below that. So if you want the star to have a higher precedence, you have to wrap that expression in parentheses. Yeah. So I think for me, moving forward, when I'm looking at complex function pointer like declarations, the rule is start at the name and then evaluate outside from there using the precedence that you have, your understanding of precedence. And you can easily, attach things. Like, let's go back to an example here. Something complex. Did they have an example here? So here, what I would say is PFA is an array of pointers to functions. That's the way I would evaluate that. Of course, this needs a void and needs a return, but you get the idea. Okay, so now with that in mind, let's go back to these examples. So X is a function returning pointer, which takes care of all this, to an array of pointers to functions returning car. X is an array of 3 elements of pointers to a function returning a pointer to an array of 5 elements of characters. So, I mean, you saw I was kind of doing a spiral there with my mouse. I think it's most important to consider precedence in order of evaluation here. So in this expression, star x bracket or even star x parentheses here, the parentheses and the brackets have the highest precedence. And so that's why they get applied first, and then the pointer gets applied second. And then because we have parentheses around this, then this bracket gets applied next to this whole expression. And then this pointer gets applied to that. And then finally, these outside parentheses get applied. And then the character is the last thing to get applied. So it is a bit of like a spiral type process, but I don't think in my mind, it's more about applying the precedence rules. So here, argv is a pointer to char. So you're not doing a spiral here. You're saying argv is a pointer, because this is a right to left evaluation for the unary asterisk operator. So you say argv is a pointer to a character. Now you can try to make up some type of like spiral thing like that if you want to, but I think it just complicates things. Here we say daytab is a pointer to an array of 13 elements, each containing an int. Here we say daytab is an array of 13 elements of pointers to an int. So I think the reason why people develop this spiral rule is because you have to bounce back and forth, and it's kind of easier to understand if you're like doing a spiral potentially, like going around, hitting a right, hitting a left. But sometimes like argv here, this is all left, left, left. So argv is a pointer to a car. It's all going left because that's the way the precedence evaluates. So, okay, I learned something from this. This is a good experience for me. I'm glad I took the time to read some of that. So we have no exercises of this chapter. There was some exercises that I highlighted for chapter 4. So let me go back and find those. Okay, I think there are just these 412 and 413, which were to write some recursive functions, which are pretty simple. But I'm not going to spend too much time on that. Yeah, I think that's all of it. Okay, we got through a lot today. All right, and then I'll probably hop off when I'm done with this for the evening. All right, so let's do a ls-la here, cd into chapter 4. I'm going to actually go back, find where my make file is, and copy chapter 5. We'll do make file and .get ignore into our chapter 04. And go in there, and here we are going to so it says adapt the idea as a print D to write. Let me actually pull it up on the screen here. So this is from page 88. So let's go back here, way back here. Oh, just passed it. 88. So it's these two exercises here. So it says adapt the idea as a print D to write a recursive version of I to A, that is, convert an integer to a string by calling a recursive routine. I'm just going to say vim exercises dot C, and we'll have a main, and we'll do our includes, and standard io.h, and standard lib. And then in here, so we need to write a recursive version of I to A. Char star here, take in a int x, something like that. And then what was the other one? Write a recursive version of the function reverse. And this will be a void because we're going to mutate it. And reverse takes in a char star s. Okay, reverse would be pretty easy. Let's do that one first. All right, so in here, I'm just gonna do some assertions. So I need to pull in my assert.h. And then down here, I'm gonna say reverse. Actually, we'll say char star s is equal to hello world, and that's going to be a reverse on s, and we'll assert s is equal to, and I can't do the equal comparison on a string, so I have to say stir equals, I think it's called stir compare, and we give it a string s with a string bang d l r o w space o l l e h. Yeah, that looks correct. And we say a man3 stir compare. This brings us back to stir and compare. I don't care about limiting it. Best practice would be to limit it. Well, I guess we can say, okay, we compare 1, 2, 3, 4, 5, 6, 7, 8, 9, stir len, stir compare of size n. So this would be stir len of s. Stir len. Stir len of s gives you back size t. I have to do stir and compare, sorry. Stir and compare. Okay. Man2 stir and compare. Sorry, man3. Okay. And then this thing says 0 if they're equal. So we're going to assert that this whole expression is equal to 0. That's fine. And since we're using 0 as a comparison, we can just put a not in front of this to simplify that. Because if it comes back 0, then we negate it to a 1, and then assert will pass. If it comes back either positive or negative, then we're going to negate that to be 0, and it's going to fail. And we can assert that not of -1 is true, and 1 is true. Just want to make sure that that comes through correctly. Okay. Yeah, so these should blow up. Let me go ahead and just do make here, build exercises. So line 17 passed. So we'll just comment that out. Oops. And then make, run it, line 18. Okay, so I just want to make sure that those both failed the assertion. So now when we run it, it'll fail because of 19. So now we get to implement our reverse. All right, so normally with a reverse, you would start with your indices on both ends, and then you would swap, and then change the pointers to be closer to each other, swap, change the pointers to be closer, swap, until the pointers are equal or they've passed each other. So that's an iterative way of reversing a string. To reverse a string like this, then we need to have a call to reverse recursive char star s, passing in 0 and the stir len of s, and we're going to return that. Oops. And then here we're going to have pretty much the same function defined, but we need to accept these two arguments, which are start, which is int, and end, which is an int. I guess technically this would be stir len s minus 1. And I'm not in Go, so I have to fix my declaration here. And okay, so this will say if start is greater than or equal to end, then we just return no work to be done. Otherwise, we are going to reverse, and I need to have a underscore r here, reverse recursive s start plus 1 and end minus 1. And we'll also do our swap here, which will be s bracket start is equal to end, and we need a temp variable. So end will save as a char temp. Then end will get clobbered for start, and s start will be recovered from temp. Okay, so that's our little swap. And then here, of course, I don't need to do that like that. Cool. Make, build, exercises, segmentation fault. Awesome. Let's comment that out for now, along with this. Make. All right, we'll do a GCC of, and say args, I think. Build exercises. Well, I don't have to do this because I don't have any args. Not GCC, GDB. Restart. Breakpoint on reverse R. Sorry, no. So I'm going to put my breakpoint on reverse R, restart, yes. P start is obviously 0. P end is not. So we say next. How did it get there? So it's that first iteration we hit segmentation fault reading from start. Okay. It's assigning it to end. So no. Quit. Nope. Quit. Quit. Alright. So S end, we copy that to temp, and then we say, hey, grab the start and write it to the end. Maybe if we pass this as a character array, but I'm pretty sure I could do that on a pointer and it'd be fine. And then take temp. Well, let's try it, make. I don't think this will work, but doesn't hurt to try. Okay, so let's run our GDB again. Continue, sorry. Restart, no. End, P start, PS at 0. Can I do that? PS 0 like this. So that's H. PS 11. So why is that? Segmentation faulting. Extra C11. I honestly don't know. Wow, I mean, I didn't think that this would be where I get stuck. Let's run GDB again. And I'll put a breakpoint on main, I guess. And then restart. No. So we're at main. We got a char star hello world. We can print out S. Print out. Okay, it's a bunch of garbage. I have to hit next. And then I can print out S. It says hello. So now we're going into reverse. So that'll blow up. Yeah, so restart. No. Restart, yes, sorry. Next, I think I have to say step to step into it. Yeah. So that goes into there. And if I print out S here, we're still there. So I'll hit step to go into there. And now print out start and print out end. And if I print out S sub start, and if I print out S sub end, definitely the characters we're interested in. So let's go to next. We assign temp. So if I print out temp here, currently it's 0. But if I hit next here, print out temp, So temp got assigned to exclamation point as we thought. If we print out S end, it's still at exclamation point. So S start. So I print out S start. It's H. So we should be able to do this. This stupid freaking thing. Like, why is this not? Oh, I know why. We're doing an assignment into a constant. It's not mutable. So I assumed doing something like this would be like, okay, it's going to be a mutable string, right? No. We have to do this, I think, to get it to be actually copied on the local stack. So now make and run it, and it works. So I learned something there. I can't declare char star with the value of a constant on the right hand side in the initialization, because that will literally point to the read-only memory. So that's the reason why segmentation fault is I was writing to read-only memory. Whereas if you do a character array and you have a right hand side a constant expression, a string literal, it'll still have that in the read-only memory section of the binary, but it'll also have a little buffer that it allocates inside the stack, and it copies the values over into it. So that makes sense. Okay, well, that reversed correctly. And this other one is I to A. Let's go ahead and write a test case for this. So we say I to A says index to ASCII of 1, 2, 3, 4, 5. And it returns a char star, so we can say assert stir and compare. And you know, I'm just gonna get rid of this thing because I'm not worried about it. Let's just say stir compare that to the value 1, 2, 3, 4, 5. Why does it not like that? Oh, what? Why does it not like that? Oh, because I forgot my parentheses here. Okay. And then we should probably do some other things like assert that negative values come through as negative, and maybe like 0 comes through. 0 comes through. 0. This will just return empty string for now to get it compile. And I don't think we need to include that quite yet. Alright, so make. So now we got some failing. Wait a minute. Wait a minute. Make. So the reason why it didn't fail is because these need to have the negative of them, because they're coming back with a positive or negative value, and that asserts correctly. So we just need to negate them. Make. Okay, yay, we got our search failure. All right, so let's go back to the book. And they were talking about some stuff here. Adapt ID is in print D. So print D prints in decimal. Yeah, prints D in decimal. So it says adapt ID is in print D to write a recursive version of I to A that is converted an integer to a string by calling recursive routines. And then if we look at print D, it takes in the same signature, but instead of being a recursive call that ends up printing out everything, we want it to be returned. I think that's the only difference here. So the advantage of doing the recursion here is that you build up the stack and then your prints go from the end to the start. We could do this something similar here, where you just say if n is equal to, or less than 0, then instead of put char, so we have print the n mod 10, which will give you the remainder. So that's saying if we have a remainder. So if we have a remainder, n 10, no. If we have a value outside of the remainder, then we're going to I to a of n10. So this whole thing needs to have a new function that it calls called I to, so we're going to return I to a of r, or recursive of int x, and then we're going to need some buffer that we pass along. So that's going to be here. We'll have char star I to a underscore r int x, and then in here we'll do this stuff. And of course I don't have to declare the type here. I don't know why I did that. And we also need to allocate up a buffer here, because int a returns a char star. Did they give us a prototype? No. Since it's C, I think having someone pass in a buffer would be appropriate. So I don't think we necessarily need to have a recursive form that's different than this. Okay, so we're going to assert the buff here. So buff is going to be char star. I want to convert this back to a char star too. Okay, so say if x is less than 0, then we negate it, obviously, and we have to insert into the buffer the value. All right, maybe we do need a recursive because we need to track the index. For now, I'm just going to call this buff is a char array of 255, and it's going to be 0 initialized, and we're going to pass it in here and buff, and buff and buff, and we're going to give it 0 to start with. We might change that. 0. Okay. Buff sub I is equal to I guess it'd be like single character. I hate when the editor does that. And then return I to A of X buff I plus 1. There we go. So that handles that case. We get that. And it has to be the 0th. So X is less than 0 and we'll just say assert here that I is equal to 0. There we go. That's just a catch in case our assertion fails for whatever reason. Okay, so we're going to say X instead of N here. If X mod 10 has a value, that means that we have values to the left-hand side of our decimal notation, in which case we want to handle those. So we say I think we do this and then say return buff here, like that. But because we're going to just be returning the buffer for convenience everywhere. Okay, here we're going to have to say buff and I plus 1. And then down here, we're going to do our insertion, which would be buff sub I. And that's going to be equal to the mod, which would be X mod 10 plus the string literal or string character of 0. It's a bit of a weird syntax, but... And then we'll just return buff here. What does this thing say? Incompatible pointer types passing char star 252 parameter type char star. That's just char star right there. Oh, it's because I took a reference to it here. That was an accident. Didn't mean to do that. There we go. All right. Let's give it a run. I don't think it's correct, but we'll see where it fails. So line 38. So it just didn't. Okay. Maybe load up the debugger. Or we can just do a println debug here. So I'm going to do my I to A here. Oh, I need to insert the null terminating byte at the end. That's the problem. We add all our bytes, but then there's no assumption that it has a null at the end. So how do we know we're at the end? We popped all of our stacks. We don't really know we're at the end. Well, we could check the I index. No, we can't check that. So say you have a large value here. You're going to do x divided by 10, which will give you 124. I don't think incrementing the index going down is going to work, because then it's going to print out. So 124 is going to go in here. It's going to advance in. It's going to print 5 from the opposite direction. So I think if we actually did a println of this, let me comment out these things. Grab this, run it, and then print f out the buff %s buff, and then I need a new line here and a semicolon, and we should be good. And I also need standard IO. Okay, so if I make that, I think it'll be, yeah, it's reversed. It's 5, 4, 3, 2, 1 exactly. So what we need to do is, instead of incrementing going down, we could decrement. But the problem is we don't know the length up front. So what we want to do is pass in a reference to this thing. I'll clean up the interface here in a bit, but in addition to the buff, we'll say int I is equal to 0. We're going to pass in a reference to I instead of I itself, just to be an int pointer. So on the first iteration, we're going to assign in here, assert that it's equal to 0, then buff sub I, and then we'll do a plus plus here. Wait a minute, that's going to increment the pointer itself. So we're going to say, hey, I, and then here we'll say star I plus equals 1. I know I can do a plus plus there, but I just want to simplify things here a little bit. And then here is just going to be a reference to I, which would be I itself. Same thing here. Okay. And then basically only when we're returning are we incrementing it. So here needs to be a star I, and then we need to increment it here. And to clean up the interface here, I'm just not going to return. I'm going to say it's a void. There's no sense in like handling that. That's a convenience thing. We'll add that later. Okay. Let's try that. Make. Hey, there we go. And we'll do a negative. Make. Oops. 1, 2, 3, 4, 5, but we didn't null terminate it, so we didn't reinitialize our. Wait a minute. That's an interesting result. Basically, it's because we didn't null terminate. but it's getting garbage, and I don't know how it's getting the garbage there, but no sense in looking at it. So what we need to do is like say like, oh, if at the very end, so we know we're not at the end here because x so maybe we saw else here. I do like the idea of handling the case where it's the 0th element differently. So maybe we'll do it like this, where we say if star I is equal to 0, then if I is less than, then we do that. Else we just do, yeah, we don't need an else. We can do it like that. So we say we're going to negate it, we're going to increment our counter, we're going to add it to the thing, and then we're going to call recursively. And then once we're done with that, the last thing we're going to do is do a final addition to the buffer, where we don't need this. Where we just add the null byte here. So basically, the first iteration, we're just calling it recursively and also handling insertion of null byte once we're done with that first invocation, I should say. So let's go ahead and make that, run it. Still gave us the wrong answer. Am I sure that make, clean, make? Sometimes the caches get, okay. It's weird because it only happened on negative value. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It repeated itself. Okay, let's go through a debugger then. GDB on build exercises. Restart, no. And we're going to set a breakpoint on I to A. Restart. So we do next, we go in here. So you print out X, it's negative. Past that, print out X. Now X is positive. Print out buff sub 0. If we do that now, go back here. Now we have a negative there. Next, print out I. It's now 1. So I'm going to step into here. Actually, I'm going to quit out of this. Please quit, yes. And I'm going to shorten this down to be like an easier number so I don't have to go through so many frames. Make restart. No. Okay, same problem. So we're going to set our breakpoint. Oh, I don't have that. So breakpoint to what? I to A, restart, next, next, next. That's all fine. Step into that. Oh, it's because I don't have the freaking return anymore. That makes sense. Can I just, yes, please go away. I removed the return. I should still have the return here. Early return. That's my bad. Okay. Yep, there we go. And then the other value was just like 0. Segmentation fault. Didn't expect that. So when we go in here, we got 0. So we say x is less than 0. Well, it's not less than 0. Then we just call I to A. So now we're in here. We say x divided by 10. That's going to be 0. So that's false. So we don't do any recursion. And then we say mod 10 would be 0 plus 0. And we assign that in. Increment 1 and return. How does that segmentation fault? Oops. Let's try. Make GDB restart. Yes. I don't care. All right, so we say, wait a minute, restart. Yes. Breakpoint on I to A. Thank you. Restart. Yes. So this one, we can skip over that. We step into that. Skip over that. Oh, we get a recursion depth issue on this one. Because you're never incrementing. Is that what happens here? Quit. Quit. Yes. Okay. So we're on the 0th iteration. So we're going to call it at least once. That's fine. Huh. Well, let's do this again. I think I might have jumped the gun on assumption there. Restart. No. Breakpoint on I to A. Restart. Yes. Next. Next. Step into it. Next. Okay, I think I got it. Please quit. Yes. Basically, if we don't increment I, we're just going to get it stuck in infinite recursion here. what I can do is do this void I to A recursive. It's going to be the same prototype here, and split this up a little bit because it's not the interface I wanted for the caller anyways. Jesus, it's taking forever for me to do this. So most of the logic's going to be moved here, and then this is going to be I to A underscore R, I to A underscore R. This thing's not even going to take in the integer, because that was just like a kludge that I did real quick to try to get this thing up and running. Okay. Why did I rename this to BR? I have no idea. So in here, we don't have to check for that condition because we already know it to be true. Or we can declare our int I here and set it equal to 0. So here, we're gonna say, hey, if your x value is less than 0, then we're just gonna go in and invert it for you. We're going to assign into the negative place in the buffer, output buffer, increment it for you, and then we're just going to go into our regular recursive thing to handle the rest of the numerical stuff. This needs to be a reference. We don't, and then at the end here, we'll just add a null byte and fall off the end. And then here, now our recursion is limited. So we just say, hey, if x is that, okay, everything else should be good now. And then if I make build exercises, okay, now it's working. All right, so now I'm going to delete these two things, and then I'm going to return buff from here, which allows us to have a char star return here, and then we can delete the third argument in the call to these, and our assertions should be good. Whether they're passing or not is another thing. Okay, they all pass. Cool. All right, problem solved. It's a good exercise. Let's go back here, vim readme, mark off chapter 5. Sorry. Okay, get status. So we got chapter 4 and chapter 5. Get it for makefile exercise, test UTF strings. Okay, get status, get CI. We'll say get log 3. We'll say get CI m. And we'll say finish chapter O 4 and 5. 5. Looks good. Cool. Git push. Pull up our GitHub real quick. All right. Looks like we got some stuff done today. 2 commits, that's good enough. I want to get a habit of doing more consistent commits every day. We did a lot of stuff on the ePulse server this day. Okay, cool. All right, we are at what page? $127. One off by one for 128. There we go. Chapter 6. So I'll pick up from chapter 6 tomorrow. And yeah, we're about a good, 128, 256. How many pages is this thing? If you exclude the reference manual, which I'm not going to, but for the sake of argument, if we just go by the chapters, then we could probably finish tomorrow. It's like 60 pages remaining of the actual like book. And then the reference manual is the beefy boy. Which I might skim through on stream. There's a lot in here. I mean, the reference manual is about that thick section at the end of the book, and this is how much we have left. It's like that. So we could probably finish the book entirely tomorrow. It's not a very big book. And to be honest, I was a little bit disappointed. I've been disappointed so far that I haven't really learned more than I thought I would. I don't know why. I thought I might pick up a few things that I wasn't aware of. But yeah, I guess chapter 6 tomorrow, and then if I count the README here, input and output is going to be read and write to files, probably some scanf, printf stuff, and then the Unix system interface is probably going to be a lot of stuff that we already know from reading the Linux programming interface. So I think this will be the last language chapter that we actually potentially learn anything about the language. And then the reference manual, standard library, and summary change. These appendices, I might skim through the reference manual just to see if there's any section, because it's a thick part of the back of the book. Just to see if there's any areas of the language that I am not familiar with, and we'll just zone in on those and then read about those. But I'm not going to read the entire reference manual. I don't think that's a good use of time. So yeah, we'll see how far I get tomorrow, but I would say end of the week, definitely have this thing done. And then we'll be moving on to computer systems, a programmer's perspective. And this book I'm actually super excited for, because every time I open it up, I look at it with some assembly. I'm going to learn a lot from this book. Like a lot. And the reason why I read the K&R C in advance of this book was to just make sure I had all of my C stuff kind of solid. Like spending that time today thinking about the complex declarations for function pointers and the spiral notation and everything, and operator precedence, all those things make it to where now I can look at a declaration and just be like, okay, I can understand what this means. I don't feel intimidated by it as much as I used to. Some of the pointer stuff I appreciated. So yeah, I mean, this is a beefy boy, and there's going to be a lot that I learn in here. Cool. So this is what I'm looking forward to next week. That'll be what I start on next week. And that's probably going to be at least a month of a time investment. So I'm going to plan out the reading and everything in advance because, I mean, honestly, it might be more than a month of time. What's today's date? It is February 18th. So it'll probably take us to the end of the quarter. And then I have a CUDA by example book that would be next, a little light reading. And then programming massively parallel processors after that. Cool. All right, I'm going to hop off here. I got a social thing to get to, so I'll be on tomorrow morning picking up at Chapter 6, Structures.